So let's go through now a couple more capacitor examples. We have two 2 centimeter diameter discs. Let's draw as we go. There's one disc, there's another disc. The diameter is 2 centimeters. They're separated by 2 millimeters. And separating those discs make a parallel plate capacitor. The electric field between the discs is 5 times 10 to the minus 5 volts per meter. I'm going to assume that this is my positive plate and this is my negative, not for any special reason, just because I have to pick one, so I'll pick that one. So there's my electric field. We want to find the voltage, the charge on each desk, and then something about what happens if we get an electron moving around between those plates. Let's start with a list of what we're given. The strength of the electric field is 5 times 10 to the 5 volts per meter. The plate separation is 2 millimeters, or 2 times 10 to the minus 3 meters. The diameter of the disc is 2 centimeters, so the radius of the disc is 0.1 meters. Already we have a little experience, and we know that all this capacitance stuff depends on the area of the plates. I'm going to go ahead and find the area of the plates. Area is pi times r squared equals 3.14 times 10 to the minus 4 meters squared. Okay, part A. What is the voltage across the capacitor? Well, we know our electric field. We know the distance between the two plates. That means we're all set to find the potential across the plates of that capacitor. We remember that electric field is change in potential over change in distance. I'm just using everything positive here because we have the strength of the field. We want the magnitude of the potential difference. So then the size of the potential difference is the size of the field times the plate separation. 5 times 10 to the 5 volts per meter times 2 times 10 to the minus 3 meters to get 1000 volts. Part B, how much charge is on each disc? Well, we know another way to find the electric field between the plates of a capacitor is that the field is the charge density divided by epsilon naught. Charge density is the surface charge density, which is charge times area. So then Q is the field times the area times epsilon naught. Epsilon naught is a constant that we know, 8.85 times 10 to the minus 12 farads per meter, or coulombs squared over newtons times meters squared. Put that through the calculator and we get a charge of 1.39 times 10 to the minus 9 coulombs. The plates are pretty small, so it makes sense that there's a small charge. Just as a bonus that you could be asked for, what is the capacitance? Well, we know capacitance is charge over potential difference. We know the charge, we know the potential difference. Another way we could find it is epsilon naught times A over D. Either way you slice it, the capacitance turns out to be 1.39 times 10 to the minus 12 farads, or 1.39 picofarads. Okay, next, this is a little bit of a throwback to our electric field section and our energy section. An electron is launched from the negative plate, so that means we throw it with some initial velocity. It goes over to the positive plate and it hits it with a speed of 2 times 10 to the 7 meters per second. What was its speed when it left the negative plate? Let's get a new sketch in there. And let's remember how we apply conservation of energy. So I'm going to go for the 2D version of the capacitors this time. So the side view. There's my plus charges, there's my minus charges. Draw in my electric field vectors. Now let's represent our electron and what's going on with that guy in our picture. So the electron starts at the negative plate. So this is our initial side. It's got some initial velocity that points this way. As it moves to the left, we expect that it's going to speed up. The electric field is to the right. The force on our electron is the charge times the field. Our charge on an electron is negative, so the force is to the left. That means our charge speeds up as it moves to the left. These are good things to have in mind as you work through. So then our electron comes all the way over here where it finishes with a final speed of VF. At the negative plate, this is going to be our initial potential. At the final plate, that's going to be our final potential. We know electric field points from high potential to low potential. So VF is the area with high potential and VI is the area with low potential. Okay, we don't know for sure we're going to need this, but it's good to get everything that you may be using written down. Let's write down our statement of conservation of energy. The final mechanical energy of our electron is equal to the initial mechanical energy of our electron plus any work done by non-conservative forces. There's nothing like friction or anything like that, so that work done is 0. Our final energy is the final kinetic plus the final electric potential equals the initial kinetic plus the initial electric potential. Okay, what do we have here? Final kinetic is 1/2 times m times Vf squared. Final potential is the charge on the electron times the final potential equals initial kinetic, 1/2 m Vi squared plus the initial potential. We're trying to sort out 1/2 m V initial squared, so 1/2 m V initial squared equals 1/2 m V final squared plus Q times final potential, subtract Q times initial potential. I'm going to work this down a little bit. So I'll take my Q outside. Now I'm going to put in two things. Q means the charge of my electron, so that's minus E. And VF minus VI, that's our change in potential, delta V. And we see that since our VF is high and our VI is low, delta V is a positive number. So this equals 1/2 times m times Vf squared minus E, so my charge is minus E, times delta V. I'm trying to find my VI, so I'm going to divide both sides by 1/2 m. Then I'll take the square root of both sides. 1/2 m goes into 1/2 m Vf squared to get Vf squared minus E times delta V over 1/2 m gives us 2 times E times m. Oops, sorry, that m's in the denominator. Scratch that out. 2 times E times delta V over m. And don't forget my square root sign. So what else do I need here? I know that my Vf that was given, that was 2 times 10 to the 7 meters per second. My delta V is my positive 1000 volts. So we found in part A that the potential difference between the plates was 1000. I know this plate is at a higher potential than this plate, so it's plus 1000. And m is the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. Put all this through the calculator, and what we get for our speed is 6.98 times 10 to the 6 meters per second. Okay, so there's a conservation of energy problem with an electron moving between the plates. We'll do one more example here. So now here's a capacitor problem where the capacitor has a very odd geometry. We take two concentric spherical conducting shells and we separate them by a vacuum. If you're trying to picture this, imagine a balloon inside of a balloon where the two surfaces aren't touching each other. The two surfaces are probably separated by some thin insulating rod that wouldn't affect the capacitance. So we have this odd spherical capacitor. The inner shell has a total charge of plus Q. With an outer radius of Ra. The outer shell has a charge of minus Q and an inner radius of Rb. Find the capacitance of this capacitor. Okay, so let's start at the beginning. Capacitance is charge over change in potential. So delta V equals the potential difference between the shells. So by between the shells, we mean between the outer surface of that inside shell, so between here, and the inner surface of the outside shell. So delta V is the potential difference between those two spots. Delta V equals. Okay, now we have to throw ourselves back to Gauss's law momentarily. So let's remember that if we have a charged object, any charged object here, let's say it has a total charge of plus Q, and we wanted to find the electric field somewhere outside at a distance r. Well, what we know is to get that result for the electric field, it only depends on the charge inside. Doesn't matter what's out here. It can be anything at all out here. The electric field is only a result of what's inside. That's a result of Gauss's law. So the electric field comes from Q enclosed only. Okay, and in this problem that's plus Q. So if we were calculating our potential, we would do minus the integral of E dot ds. I'm not going to go through that part here. We would do that work and it would bring us to the result that our potential at some distance r was equal to k times q over r. So that's the result we get when we know that our electric field is due to what's inside. The potential outside the shell only depends on the charge inside. Okay, let's look at our example now for our spherical capacitor. The potential at the surface, Ra, so V at Ra is equal to K times the charge inside, so we're given that that's plus Q, over the distance Ra. Our potential at this inner surface Rb, so this is before we get to the place that carries charge negative Q because we're on the inner surface of that shell. Our potential here only depends on the charge that's inside, and the charge that's inside this distance here is plus Q. So that's our potential at position Rb, which is on the inner surface of the outer shell. So we're going to do Q is capacitance C is the net charge Q divided by the change in potential. So my change in potential is going to be my potential difference between surfaces A and B. So I'm going to do the potential of A, subtract the potential of B, and I'm going to get K times Q over Ra, subtract K times Q over Rb. Okay, I'm going to put this in here for my delta V, and then I'll divide that into Q, and we'll see what we get for our capacitance. So I've got my KQ outside of 1 over Ra minus 1 over Rb equals, right off the bat, I notice my Q's cancel. So I've got 1 over K. I'd like to simplify this guy a little bit. If I multiply this one by Rb over Rb, then I get Rb, and I multiply this one by Ra over Ra, I get Rb minus Ra divided by Ra times Rb. Just finding a common denominator there. Next, I'm going to put in that K is 1 over 4 pi epsilon naught. And then my denominators of the denominators become my numerators. So I've got 4 pi epsilon naught times Ra times Rb over RB minus RA. That's kind of a neat result for a spherical capacitor. So even if we have a bit of an odd geometry, if we start from capacitance as charge over potential difference, we can get to our answer.